We're now ready for part 2 of lesson 3.4. And our previous lesson, we spent some time reviewing how to solve quadratic equations using a factoring method and also using the quadratic formula. So that's going to be important for today's lesson. When we start to actually apply, we're going to start looking at quadratic functions in a real-life context so we can determine certain questions, answer certain questions. And then we also looked at properties of parabolas in the previous lesson where we determined the axis of symmetry. We determined the vertex, whether there was a maximum and a minimum, and then what was the value of the max or min. So all of that review was necessary. Those skills are going to be necessary as we get into more application problems in this lesson. So let me give you a few examples like the ones that will show up on your assignment. All right, so this first example is a pretty typical real-life example, word problem, of a quadratic function. All right, notice that it's a function of height. All right, we're talking about a ball being kicked in the air. Its height above the ground can be modeled by this function. So obviously, height is a function of time, okay? And it's not really specified. We know the height is in meters, and time is, we'll just assume it's in seconds. So how do I solve this problem? Well, let's think about the graph. We know because there's a negative in front of the quadratic term that this is going to be a parabola that opens upside down. And that probably makes sense because that's pretty much the flight of the ball. It started on the ground, it was kicked, it reached a maximum height, and then gravity took over, and then it fell to the ground. So in graphing purposes, if we put this on an XY plane, we have the t-axis, which represents time in seconds. And then we have the y, or in this case, the h-axis, which represents height. H of t is the height of the ball. And we want to know basically how long did it take to complete this path. So when you're asked to find how long it took for an object to, when it left the ground, to come back to the ground, if it started on the ground, then what we want to do is put height of 0. Because if you think about it, we're going to be solving for these two numbers that represent time. Okay? And the thing that's true about both of these values is they represent when the ball is on the ground. And when the ball is on the ground, it has a height of 0. So we're going to make 0 go in for h of t. So we're basically going to solve a quadratic equation. And we get to pick a method. Your method of choice will be either factoring. I like to do factoring when it's possible. Or you can do the quadratic formula as well. So this actually does factor because 4.9 does divide evenly into 14.7. So to keep my quadratic term positive, I'm going to factor out negative 4.9. And then t is in common to both terms. So this is factoring out a GCF. And then when I divide negative 4.9 into both of these terms, I get t, and then negative 4.9t divided into positive is going to make a negative 3. Okay, and so solving by factoring means we let each of those factors become their own little equation, and we solve. So we got two numbers. Now this one makes sense. At time 0, that's saying, okay, before the ball was kicked. At time 0, it's at a 0 height. That makes sense. But then this is really what we're after. How long is it from here, time 0, to this point? And that other point is 3. So to answer the question, how long was the ball in the air? It was in the air for 3 seconds. Okay, what is the maximum height? Well, now we're talking about the vertex. And the vertex uses, to find the vertex, we use a really valuable formula to help us find something called the AOS, the axis of symmetry. So here's the formula that we use to find the axis of symmetry, and just to review a little bit, the number in front of the quadratic variable is A, we call that A, and then the linear term coefficient is called B. So we need the AOS so we can find this maximum height. So it's going to be the opposite of 14.7 over 2 times negative 4.9. All right, so be careful with the opposite of. Sometimes people forget that, and that obviously is going to throw your AOS value off. So let's find out what the AOS is if we plug in. So 14.7 divided by, and then we'll want to put this denominator in parentheses. 2 times negative 4.9. Okay, so if I just did the parenthesis part on the inside, I get negative 1.5, but the formula calls for the opposite of that number. So the AOS is the line x equals 1.5. But that doesn't tell me the maximum height. That basically is going to be the answer for letter C. Letter C is how long in seconds did it take to reach that maximum height. That's going to be, let's go ahead and answer letter C. But to determine the maximum height, we're going to have to plug that number back in. We're basically doing h of 1.5. So replace the 2 t's with 1.5. And then go to your calculator. And when you key this in, make sure you use parentheses correctly, and don't forget the negative. So when you key this in, you should get 11.025 meters. And we already answered, this is the AOS. That's how long it took to get to that point. Okay, so then this one problem, you do what you're typically asked to do for all of these. It's either find the time that an object is in the air, that's pretty common, or you're finding either the maximum or the minimum. If it's an object, it's usually maximum, but there's some business applications where we're interested in finding the minimum value. But both of those involve finding the AOS and then plugging that AOS number back in to your equation. All right, let's take a look at our next one. A rock is thrown. If a rock is thrown downward with an initial speed of 32 feet per second, the distance is given in t seconds, given by this function, distance as a function of time. So if the rock is thrown from a tower, top of a tower that's 128 feet tall, okay, that's our distance from the ground. How long does it take for the rock to strike ground? So we're solving for t. Okay, so let's put 128 in place of d. And then we're going to be solving a quadratic equation again, so we need to make this equal to 0. And then you can pick a method. This one's factorable as well because 16 goes into 32 and it goes into 128. So that's my preference. I like to do factoring. So let's factor out the GCF of 16 first. And 128 divided by 16 is 8. And now I'm going to factor this quadratic trinomial because the factors of negative 8 that add up to positive 2 are 4 and negative 2. Okay, so the two factors that contain t, I get some people sometimes that are hung up with the 16. Well, what about the 16? Well, we're solving for t, and factoring out the 16 helped us get there, but you don't have to set 16 up as in an equation. You're just solving the two factors that have t, so we get two values, but notice one of them is negative. So negative time does not make any sense. So in cases like this, and this happens occasionally where you're solving a quadratic and you'll get a positive and a negative, you're just going to throw out the negative value. We only are concerned with obviously positive time. So the answer for letter A would be 2 seconds. Okay, well, they changed the scenario just a little bit. What if the tower's 48 feet tall? So this time we'll just put 48 and we'll solve and see what the difference is. So again, if you prefer the quadratic formula, that's fine. I'm going to do factoring because again, 16 is a GCF. And we can factor this quadratic trinomial. The factors of negative 3 that add up to 2 are positive 3, negative 1. Again, I get two answers, but in real life, no such thing as negative time, so I'm throwing that out. So if the tower were 48 feet tall, it would take 1 second to strike ground. Okay, example number 3. For a certain population, the growth rate in thousands of individuals per year depends on the size of the population. So we're given this important function to help us answer this question. The population is stable when it is neither increasing nor decreasing, or in other words, when growth is 0. So at what level is the population, which is n, stable? All right, so it's kind of what we did before. I'm going to let g be 0. And this time factoring isn't possible, so I'm going to do the quadratic formula. You just have to be careful. If you want to turn this around so that you can see it in standard form, that would be okay. But this is a, negative 0.2 is a, b is 1, and c is 1. All right, so we're solving for n using the quadratic formula. So the opposite of b, plus minus the square root of b squared minus 4 times a times c. And all of this is going to go over 2 times a. And you go to your calculator and make sure you're able to use your calculator correctly in problems like this. So you're going to get two answers because you got to do the negative 1 plus this radical, hit equals, and then divide by negative 0.4, and then you'll do negative 1 minus this radical. So hopefully you're good with using your calculator. After yesterday's or the day before our previous lesson, you're good with the quadratic formula. You're going to get two answers here. So make sure you're able to get both of these answers. So again, the context here is number of people, population. There is no such thing as negative population. So we're going to go with the positive result, and then we would just answer it using a phrase. It's stable when there are about 5.85, this is in thousands, people. When there are about 5.85 thousand people, that represents stable growth. Okay, on to example number 4. Here's a business type function, a revenue function in particular. Suppose that the manufacturer of a gas clothes dryer has found that when the price of the dryers, P, when we have a certain price, this is how we get revenue. So revenue is just a fancy word. If you're not familiar, that's the money that is taken in. Now that's we have expenses that come out of that, we have taxes that come out of that, but this is just pure money from sales. So what unit price should be established for a dryer to maximize revenue? Very important question that businesses will need to answer. So here we are again. If you see maximum or minimum, you're thinking vertex. How do I find the vertex of this parabola that opens upside down? Well, it starts with finding the AOS, opposite of B, over 2 times A. And this is actually going to get us the price. Okay, so when we do the opposite of B over 2A, or find the AOS, okay, if you think about it, if this were graphed, the x-axis would be the input, that's the price. So when we find the AOS, we're essentially finding that price that will maximize revenue. So $500 is what comes out of this formula. And then the y-axis is actually the revenue in dollars. All right. So what is the maximum revenue? This is when we're going to plug this AOS number back in. We're basically going to say revenue input $500 will be what? What is the revenue if my price for the dryers is $500? Okay, so you put that in your calculator, and hopefully your result is $1 million. We're going to bring in $1 million from sales if we price our dryers at $500 each. Okay. Number 5, a fireworks distance noted by T in meters from the ground is given by D equals, this should be D, sorry. In meters from the ground is given by D equals negative 1.5 t squared plus 25 t. T is the number of seconds after the firework has been lit. So letter A wants us to find out how many seconds have gone by once the firework is lit until it explodes. So if it explodes at its maximum height. So we're assuming this is basically how long does it take for the firework to reach maximum height, because that's when it's going to explode. So here again, we're doing a vertex problem. Find the vertex. All right. So the opposite of B over 2 times A. So you go to your calculator and you plug this in, the opposite of 25 over 2 times negative 1.5, and you're going to get 8.3 seconds. That's how long it takes to reach its maximum height. And then what is the maximum height, or when it explodes? So now we're going to replace the t's in our formula, in our function, with 8.3. And we'll go to our calculator, and you're going to get about, when it explodes at its maximum height, it is about 104.2 feet. I say about because we'll round it off. Okay, let's try another one. The height in feet of a certain aircraft, t seconds after it leaves the ground, is modeled by that function. Find the maximum height. Here we are again. What's the maximum height? So we're going to find the AOS, opposite of B, over 2 times A. And that's going to end up being 32.5, which is the answer for letter B. This is how long it took to reach its maximum height. We'll say 32.5 seconds. To find the maximum height, we're going to have to plug that number back in. And then we add this big number. Okay, so you're going to go to your calculator. This is basically h of 32.5, inputting for time. And we'll see if you can come up with the number, plugging all this in. I left off the squared here. All right, I think we got it now. So all of this keyed in. Don't forget the, messy. Don't forget to square. And the result of keying this into your calculator should be 30,000 feet. That will be the maximum height, and it's going to take 32.5 seconds to reach that height. Okay, we have one more. And we're told here that a carpet is 7 feet longer than it is wide. So we'll just do a little visual here. Okay, so I'm going to call this width, just given width a variable, because the length should be 7 feet longer than this. So the way I represent 7 feet longer is I take width and I add 7. If an area of 50 square, if it has an area of 50 square feet, so I guess a little review of area of a rectangle is area is length times width. So if we have an area of 50 square feet, what are these dimensions? So we're going to need to literally multiply length times width and make that equal to the number 50. So I'm going to do the distributive property. I'm going to make this equal to 0. And we're going to pick a method. Factoring isn't possible. So it looks like we're left with a quadratic formula. If you remember completing the square and you'd like to do that, you're welcome to. So let me just show you what the quadratic formula would look like, and then we'll go to your calculator. So the opposite of b plus minus the square root of b squared minus 4 times 1 times negative 50. All of this over 2 times 1. So don't forget, it's going to be 49 minus, this is negative 200. So 49 minus negative 200 is really plus 200. So negative 7 plus minus the square root of 249 over 2. So you need to come up with both of these answers, the plus and the minus. Okay, again, reviewing our previous lesson. And you're going to get a positive and a negative. So 4.4 should come out. And then a negative 11.39 should come out. But since we're talking about dimensions, no such thing as negative dimensions. So we're going to go with the 4.4. So 4.4 will be the width. And then 4.4 plus 7 will be the length because it's 7 feet longer. So we'll say our final answer here will be 4.4 feet by 11.4 feet. Those are our dimensions for the carpet. Okay, that is it for the notes. This should give you enough examples to help you with the assignment. If you still have questions as you're working on the assignment, please let me know, and I'll see you next time.